Hello, everybody. So this is E340, E599, lecture 14. Remember that it's being recorded. Let's see, I am at home and my internet at home is not always terribly reliable. So if I drop out, I guess either James or Giuliano will have to take over. My internet's been okay for the last few minutes. We'll see if it lasts. There's two references on the slide here, and I believe the slide deck is on the slide share. I believe you should have access to the slide deck. There's two main references there if you're interested. So this is what we're going to talk about today, and I think we're going to go back over to James for the student updates. You want to do that, James?
Right, so I just wanted to go around the room quickly. Again, if somebody has a slide to share, that's fine, but I wasn't expecting it. Let's just quickly hear how people are doing. And we do have to come up with a schedule. So in particular, I need 3 volunteers to talk next week. And I understand that you may not be 100% finished if you're speaking next week, but I think, well, we have to get at least 3 people done next week because we're not going to be able to get everybody in on the 15th. So let's have a quick, if anybody volunteers for the 15th of next week, that's fine. Otherwise, we're going to have some kind of Dutch option on it.
I don't mind going next week.
Okay, Mercedes, thank you.
I can go next week as well.
Sorry, who was that? Who else was?
Tyler, I can go next week.
Right.
And I can also go next week.
Oh, great. Thank you, Colin. I know. Okay, and then does anybody else want to go next week, or would the other people prefer to go on the 15th? I'll take the silence as that they prefer to talk on the 15th. Okay, so let's just quickly go around the room. Antonio, how are things going on the project?
They're going pretty well. I have a paper picked out with a pretty in-depth model of tuberculosis. So I've been kind of simplifying it and running with assumptions that populations are only adults or populations only experience the fast latency tuberculosis. It has a built-in treatment regimen, a treatment node. I think I'm going to add in another one to kind of see how resistance develops and the population of people that have resistant tuberculosis versus those that don't. Other than that, I've just been kind of playing around with some sliders and some of the variables, and I'm just seeing how they kind of affect the overall graphs of people entering treatment and recovery.
I think that's something that if we can get that into a nanoHUB, I think people would be very interested in that. Drug-resistant tuberculosis, big problem. Mm-hmm. And so exploring that is really interesting. That's great. Jeffrey?
Yeah, mine is going well. I have implemented the equations with the coupling terms, so yeah, and it works, so that's good. Yeah, I mean, it is working well, I think.
That's fine. Again, if people want to meet with me on Wednesday, Thursday, Friday, I'm available. And Josh will be back, so he's also available.
Okay.
And Giuliano can help us debug uploading to nanoHUB too.
Okay.
There are issues with that. Great. Okay, Kali, if you're volunteering to go next week, I guess things are going okay.
Yeah, things are, I would say, overall going pretty well. I also just kind of wanted to force myself to have this project done a bit sooner before finals week hits, so I have my Jupyter notebook outline based on what the project requirements are. So right now I'm just filling in that information. I think I have the 2 baseline models almost down. There are a couple paper replication things that I'd probably set up a meeting with you about. And then other than that, I still have to I want to write some code that answers specific questions regarding COVID vaccination. So right now it's just like we have the models, we can play with parameters, but then I still have to implement the walkthrough of, oh, how do we determine how many people need to be vaccinated, or what happens if we have a limited amount of vaccine, like those specific questions. So that's where I'm at right now. I don't know if you I don't know if you wanted to see the Jupyter notebook, but it's just
If you
code.
want to screen share, you're welcome. You don't have to. It's up to you. I could certainly give you the screen if you'd like to show it.
Sure.
Okay, so you should be able to screen share.
So here it's like we kind of I have headings for all the different components of the project. So the biological background, the mathematical background will go in here. And then I did the parameter fitting. I didn't know if it would be useful to include this in the application if people want to see for themselves how I did it. So that part is done. Obviously, I still have to run all the output. I did this originally in another file. That's all here. I used data from the Johns Hopkins University, their COVID tracking project. So that's all that. Then that doesn't consider vaccination. So now once we have the non-vaccinated variables, we go into an SVIRS model. I should probably add a D here, but the original paper didn't have that in it, so I didn't include it as of yet, but it wouldn't be a big deal to do that. Here's the model there. Here's all right, this is when I try to replicate stuff from the paper. We don't have to talk about that right now. And then here's the model again with the fitted parameters. Here's where I'm going to insert the sliding scale of all the different parameters you can adjust. Then the next level of complicatedness is the SVEIRS model. So this is a different paper. And then here's the outline for the rest of it.
Great. I think you and Brian are working on sort of slightly similar things. It'll be very interesting to see how they compare. Because the vaccination is a fascinating problem.
Yeah.
And again, I think everybody has projects where if they're put up on nanoHUB and you have enough. The key thing for a nanoHUB app is to have enough introductory material that people read it and want to run the code.
Right.
So so think about it that way. If you were browsing the internet and came across a little app, what would intrigue you so that you wanted to run it? And that's not for you particularly, but for everybody. But that looks great, and that's good progress. Thank you. Tyler?
Yeah, my project's going really well. I'm doing influenza A, and my paper has data for 6 different patients. And right now I have the model replicated for both, like there's 2 models. There's a simplified version and a version that includes an implied immune response. And right now I have models replicated for both of those. And I plan on extending the model to specify the immune response. So I'm gonna play around with that for the week. And I have sliders to mess around with the parameters and such.
Okay, that's great. And again, if you have any issues with how to present it, sliders, we can talk. Josh is good at this, so that'd be great. Okay, I'm pleased that people are making progress. I should have said Happy Thanksgiving before we started, but I guess I hope people got some rest. Devin?
Yeah, so I did end up deciding to change the paper that I was replicating a couple weeks ago. The other one used a lot of dynamic modeling. It was very tough. So now I'm doing Ebola modeling in Liberia, which isn't quite as prevalent of a disease, but it's still interesting for possible future cases and stuff like that. And so this paper talks about the effect of media impact and vaccination. So right now I'm looking at pre-media stuff. So the disease is going to spread faster because people aren't informed about how to take precautions and stuff like that. And then I'm also looking at the effects of vaccination efficacy and the vaccination rate. So I have some sliders implemented for that. And so now I just want to do some parameter sweeps for some other variables. And I've thought about doing some minimization fitting. And that's where I'm at now.
So I think we have 3 people thinking about viruses and vaccination. So it might be not a bad idea to have Kali, Devin, and Brian. If you could set up I don't have to be there, although I could be. If you could set up a fun conversation, maybe compare some notes about how you're thinking about presenting it. Because I'm sure each one of you has different insights into how to present that material. And maybe we can learn from each other a little bit before you finalize your projects. You don't have to, but I think it's interesting. Ebola, certainly we should be glad that at least that Ebola isn't airborne transmissible, and that COVID doesn't have the lethality of Ebola. That was, I mean, it's got a very different dynamic because it's so rapidly lethal. So it's quite interesting because it's a very different disease. Wonderful. Brian, how are you doing?
I'm doing all right so far. I've mainly this week and last week, I was just finagling with a lot of the parameters and kind of just testing out how different sliders could operate in the model. I could also look into like, I was thinking that we could meet this Sunday and probably like wrap or flesh things out a little more. So that's where I'm at.
It's fine. I mean, again, there's no people, your classmates are good resources. So you shouldn't, you can't force people to talk to each other, but I encourage you to do that, especially if you have 3 people interested in that problem. Mercedes, how are you doing?
I'm doing all right. I'll have a decent amount to do to be done or to be presented by Tuesday. But again, like Kali, I'm trying to motivate myself by updating my deadline. I need to work on getting the immunotherapy component of the model working right. When I tried to update that one equation, it caused the cell deaths to not load right. So that's where I'm at right now. And then I'd like to add some sliders and everything to make a nanoHUB app visually pleasing. So
Okay, well, maybe Josh and I can meet with you tomorrow or Thursday and help.
yeah, Thursday would be great.
Okay, good. Well, it sounds like everybody is making progress, which is the main thing. Thank you. Sorry if the email I sent out suggested that everything was supposed to be done today. I didn't mean. I really did want to just have to make sure that to check in, reserve time to hear where you were and if you needed help. That sounds like people are making progress, and I'll be available to help out, and Josh will as well, and Juliana. So Jim, it's back to you.
Right. See my screen share up.
Okay. Yeah, that's
Is my
fine.
screen- Okay, looks good. Okay. So a couple quick definitions. So pharmacokinetics, there's actually a lot of terms that get kind of thrown around. They overlap. Sometimes they mean the same thing. Sometimes they mean different things, depending on who's speaking. Pharmacokinetics is what we're going to call it. Pharmaco, you could replace the pharmaco with nutrient or toxico or any of another number of other things. So it's not just for pharmacological agents. It could also be for an environmental toxin or for a nutrient. In fact, you could do a PK model for oxygen from the lungs if you thought that was needed. But we'll stick with pharmacokinetics. So pharmacokinetics describes what happens to the drug in the body. It's absorption, distribution, metabolism, excretion. We'll talk about that a little bit more in a minute. It's used to predict how changes in dosing affects changing in the blood, how the concentration changes with time, how factors like change in body weight or change in dose or frequency of dose or route of dosing will affect concentration in the body. Usually in the pharmacological domain, you're worried both about getting a pharmacological effect at the same time staying away from toxicological effects. So you don't want to get into a domain where you're going to have toxicity associated with the drug. The basic data for pharmacokinetics is just to follow the drug concentration versus time in the plasma. Notice that's not the blood, that's the plasma. The plasma is the component of the blood minus the red blood cells, and actually all cells, but blood is by volume almost 50% red blood cells. And a little more than 50% is plasma, and it's usually what is followed. The nice thing about following drug concentration in the blood is that you don't have to sacrifice the individual. It's not invasive. It doesn't take very much material. So that's the good part. The bad part is it's just the concentration in the plasma of the blood and not concentration in tissues or in other places where you might be interested in it. So PK is used to help predict drug disposition. It's used in support of discovery and development and drug registration. You usually, these days, you usually have to include a pharmacokinetic model with a new drug application to the FDA. It's used in clinical therapeutics. It helps to calibrate doses, especially for drugs that have very narrow therapeutic windows. Therapeutic window, the therapeutic index of a drug is the ratio of the toxic dose divided by the therapeutic dose. What you'd like to have is that ratio to be very, very large, in hundreds or thousands. With many drugs, that ratio is closer to 2 or 3, which means at 2 or 3 times the efficacious dose, you start to get significant toxicities. So like I mentioned, so it applies to toxicology and toxicokinetics. It's used in interpretation and planning in drug development. It's also used in interpretation of toxicology studies. For instance, chronic exposure to PCB in well water or drinking water. How does that build up over time in the blood and in the tissues of the body? So those are pharmacokinetic type models. So it could be a drug, it could be a repetitive exposure to something that's in your environment. So disciplines related, clinical pharmacology uses extensively. Drug research and a few other areas uses PK, and toxicological research uses it to a fair amount. US EPA uses it quite a bit to try to estimate in vivo doses or in-body doses based on environmental exposures to toxins. I think I'll skip that one right there. Go to this one. So PBPK is a kind of an extension of it. This is physiologically based pharmacokinetic modeling. And it's very old. This is a nice slide from Sarah Queenie. One of the very first papers was 1937, back when they had to integrate their ODEs by hand. That model actually is pretty much how it's done now, a blood circulation loop that's going past tissues. One of your tissues is an input. Some of your tissues are outputs or clearance modes. This is a kind of an overview of scales of modeling. I think James has probably presented something like this in a class already. We have scales from the right of subcellular reaction kinetics, signaling gene transcription, moving up to how cells interact with each other, moving up to tissues, moving up to organ, and finally up to the whole body and the population to a larger scale. Well, the computational modeling technology at the whole body scale is usually PK or PBPK. So you're treating the body as a set of compartments that are coupled primarily by the blood, but there can also be coupling from lymph and other flows like airflow in the lungs and upper nasal. So mostly we're going to be talking about this left-hand most biological whole body scale. If you make replicates of the whole body scale, you would get a population scale model. So we'll do a little bit more of a definition. The term is usually ADME, sometimes it's LADME. This is the clinical data that you collect. And so L is liberation. And up here in the upper right, it actually should be in the gut probably, but if you have a pill, for example, how long does it take the pill to dissolve? Absorption is how rapidly the drug is absorbed from the gut, which is what we're going to be talking about, but it could also be the lungs or the skin or wherever else you're actually dosing the individual. Some drugs are largely absorbed in the stomach, some are absorbed in the small intestine. So there's absorption plays a big effect on how rapidly something gets into the body. Distribution is how it moves about the body, usually, like I said, usually covered by or carried by the blood, sometimes other fluids like lymph. Metabolism, not all compounds, of course, are metabolized. Most are. Metabolism can occur in just about any tissue in the body. The liver and the kidney are the two most active metabolic sites, though other tissues will do it as well. Metabolism basically generates a new compound, which you could also apply PBPK to. So the metabolite of a compound now has its own PBPK model showing how it moves about the body, how it goes to the clearance organs and things like that. And then finally, excretion, which is usually via the urine. The kidneys filter it out and put it in the urine. There's also excretion of compounds being pumped back from the liver into the gut. There's various possibility of varying amounts of excretion from respiration from in the air you exhale through the skin. In general, though, it's the kidney and the liver that are doing most of the excretion. Basically, just taking the compound out of the body. So this ADME type study is the most common thing done clinically and preclinically because it's cheap and fast. And the typical data you get, I showed it earlier, so a graph of time, plasma concentration versus time. So this particular one is for APAP, which is acetaminophen, which is Tylenol and a few other drugs. It's an anti-inflammatory analgesic given orally. And this is a typical oral absorption curve, some relatively fast rise to a peak in concentration at a particular time, and then usually a much slower decay. Other routes of dosing are shown here. So this is for the oral dose through the stomach, through the small intestine and the colon. But there's also dosing via intramuscular injection or intravenous injection. There's several other injection sites, intraperitoneal, which is into the abdominal cavity. There's subcutaneous, which is just under the skin. Each one of those has kind of a fundamental curve. Intravenous gives essentially an instant rise in blood concentration. Subcutaneous and other non-bloodborne injections tend to give a much slower rise. Pulmonary delivery through the lungs with like a respiratory delivery typically give very fast. The decay is a function of the compound primarily. It's usually much slower. So what we wanted to do today was to try to step you through building in nanoHUB Tellurium a simple PK model, and then kind of jump forward and give you an existing PBPK model of the whole body and let you play around a little bit with it. So this is the simplest pharmacokinetic model. Again, part of this layout is, and the reason the blood is here in the middle is because that's where you can sample from. You usually can't sample at any of the other sites. So the compound is in the blood. It gets into the blood from absorption from the gut. It's excreted from the blood or cleared from the blood in the simple model just via the kidney. And the compound in the blood is at equilibrium with the bulk of the body, with the organs, the tissues, fat, and so forth. This typical SBML ODE type model. So each one of these compartments has a defined volume. It's the volume often is the blood volume of the organ. However, in simple PK models, it usually doesn't quite work out that way. Only the blood compartment has a volume that would be equal to the blood volume of a human or experimental animal. In humans, that's about 6 liters. The volume of the body is usually somewhat adjustable. Figure an adult human is probably 65 kilograms, which would be 65 liters. And the kidney as a clearance compartment doesn't really matter too much what its volume is considered to be. Transfer between the compartments is usually assumed to be just based on concentration difference. There is the complexity of transporters, both importers and exporters, but we're not going to talk about that very much. You might run into them in some of your research, P-glycoprotein and other exporters, which are membrane-bound pumps that take small molecules out of cells. So the small molecule passively diffuses into the cell, and it should equilibrate with the extracellular fluid. But because of the presence of the pump, the multi-drug resistant pumps, it gets pumped back out of the cell, back into the blood, or back into the interstitial fluid. So there are complexities about the system that are usually very compound dependent. We're going to take a simpler approach and just say that it's passive diffusion and driven to try to equilibrate the concentration between the blood and the tissue. So as I said, concentration-driven transport, compounds assumed to equilibrate in terms of concentration between the blood and the body compartments. And it's the delta concentration that drives the transfer. We're going to be using tellurium. Tellurium doesn't really treat units. So tellurium will never warn you if you're mixing units, if you've got seconds in one place and minutes in another place, or moles in one place and grams in another place. It's important to keep track of intensive versus extensive variables. So intensive variables are concentration in general. The nice thing about intensive variables is that they are scale independent. So the concentration, if you're talking about 6 liters of blood, is the same thing, is the same numerical value if you're talking about 1 microliter of blood in a capillary or something like that. So we have our intensive variables that are things like concentration. We also have extensive variables, which are typically sums, so grams, moles, could also be liters if you're talking about the total volume of the blood. The SBML standard, which I hope you guys have probably heard about, even though you're not really using it so much in tellurium, by default uses extensive variables. Tellurium, by default, uses intensive variables, but you can change that, and we will. Transfer in the model is driven by the intensive variable of concentration. And we'll talk about it more in a few minutes, but the challenge is that the actual fluxes can't be calculated in concentration units because the compartments don't have the same volumes. So there's some bookkeeping that you have to keep track of, and that's part of the reason why it's important to always keep track of your units. You should have your units written down someplace. Even if your programming environment doesn't actually treat them as data, you should at least have it in comments. So we'll start off with a real simple one, just the transfer between the blood and the body, assuming that you start off with some amount of material in the blood compartment. So one thing we need to do to start with is assign a volume for each compartment and an amount, an initial set of conditions, amount in the blood, the amount in the body. Again, we have this problem of whether you're talking about an intensive or extensive parameter. So dx dt, where compound X is the extensive amount, and square brackets meaning concentration is the intensive amount. And the equations look very similar, but obviously they have different units. And so you have to be careful that you're not mixing them inadvertently. So in general, like I said, compartments will have a volume. In general, the volumes are different. Because the volumes are different, you can't treat the transfers using changes in concentration. You need to treat the transfer as changes in the extensive quantity, and then recalculate the intensive quantity after you do it. To put that another way, when you say compounds coming out of the blood, you say it's coming out at so many grams per minute. You can't really easily say that it's coming out at it's decreasing the concentration in the blood of 1 millimole per minute, because the 1 millimole out of the blood won't be 1 millimolar out of the blood won't be 1 millimolar in the body because the body compartment is so much bigger. But if you say 1 mole or 1 millimole transferred, instead of that will work, but saying 1 millimolar won't work. So you got to be careful about that. So as an example on how you can kind of fix things up, you want the change in concentration. So this is a blood to body transfer equation. So the change in concentration in the blood is the rate constant based, and then the difference between the concentration in the two tissues, expressed though as the amount divided by the volume of that compartment, the amount in the body divided by the volume of the body. And then the body blood constant just switches things around. You've got a forward and a reverse rate. If you treat it as a equilibrium process, then you just have a equilibrium constant. We'll talk about that a little bit more in a few minutes. So what we'd like you to do is to start up Tellurium and try to build this little model in Tellurium. So I'm going to make a new one. So everybody can get Tellurium running. And from the little talks you gave, it sounds like you're fairly familiar with Tellurium. So we'll need to start with, and I'm going to go back and forth between an existing model because I don't use Tellurium all that often.
All of
So start
those,
off with,
all those simulations should be available for upload in the shared directories and also on Canvas.
right, let me turn the light on, it's getting dark. So the big one is import Tellurium, and you may or may not need some of these other ones that I have on this particular run. Okay, so you need to define two compartments, call it blood and body. And that's this here. Since this model actually came out of an SBML model, it does have units defined. I would recommend that if your tool doesn't use it, at least put a couple of comments. What's your time unit, hour, minute, seconds? What are your mass units? You're working in moles or grams or milligrams? And what your basic volume unit is. So we're going to define two compartments. Compartments don't have to be constant, usually are. And we'll do blood at 5 liters and body at 65 liters. So that would be 75 liters, which would be a 70 kilogram person, which is, what is that? 170, 180 pound person. You'll also need species. This is a little, if you're used to reaction kinetics, it's a little different because basically you have to define separate species, even though they represent the same thing, but because they're in different compartments, they look like different things. So we have species compound X in the blood, and it's in the V blood, and V blood is what we had named our compartment. So compound X blood in compartment V blood, and then compound X body in compartment V body, V body. This is a little bit of nomenclature requirement that we're going to, both of these species have only substance units. That's to make sure that Tellurium is not switching back and forth, switching over to concentration units when we want it to be using mass units. You want to use the extensive variable, not the intensive variable. Okay, now as we had there's our ODEs, blood to body, body to blood, concentration in the blood, this ratio of the amounts in the two compartments, the delta times the rate constant. And so that's just explicitly there. And then the same thing with the reverse. So this X body minus, so this is exiting the body, going back in the blood. This is exiting the blood again because we have the minus rate constant. And in our equations, when we have a forward and reverse rate, so just back to our forward and reverse rates. And we'll just set them both to 1. And again, great place to stick in what you think your units are. Even though Tellurium's not going to actually explicitly be using the units, at least write down when you define the variable what you think the units are. All right, that gives us the basic layout, and now we want to, initialize, set our initial conditions. And that's here, and I have a little note about, oh, sorry, down here. That initialization doesn't necessarily respect the substance only flag. So we're initialize the blood concentration as 1, essentially, and then divided by the volume of the blood compartment, which we had defined as 5 units. And so this is the very first check you need to do, is to make sure the model starts up at the value you think it should. And it'd be a good place to find out whether or not you need to correct for volume of the compartment. Okay.
I do you want to check to make sure everybody's able to replicate that? Just to
Yeah.
go. Any questions or people need help getting that to work? I usually use the poll. If you hit the poll button at the bottom of the control window, you can it asks a set of questions about whether people are done or need more time, so that way it helps stay synchronized. I don't know if you can see the polling.
Yeah, I can.
Okay, great.
So while people are still kind of working on that, I'd say something that one challenge in Tellurium is that you can't actually define what anything is in a robust way. In this case, we're just calling our compound X. It isn't actually explicit anywhere that this is a compound. It could be, yeah, literally could be, it could be heat, it could be temperature. We could be doing a heat transfer model with a bunch of ODs in it. So Tellurium doesn't let you say X is a compound. It also doesn't let you say that the compartment we call blood is the blood compartment. These names are relatively suggestive of what they are, but it would be nice to put in a more formal definition. This is human blood compartment, and this is the human body. Other SBML-based tools will let you do that, like Copasi. But today we're working in Tellurium. And I don't know if you've seen it before, but this single apostrophe means we're defining an explicit ODE instead of writing it in the more Jarnac-like way of doing an ODE. Okay, I think I'll move on. So, where am I? There we are. So let's just reiterating what we were putting in and what was in the sample code. If you run a time course for 30 time units, there's the, if you have a copy of the slide deck, there's the whole Python, Tellurium Python. So it should give an output like this, and we'll actually see if mine does that. Yeah, it does repeat it. So I'm gonna use my slides. So our concentrations in the blood in the body and our total amount in the blood in the body, you see there's pretty big difference in just the magnitude of the number, so it's a little hard to pick out. But if you just look at this bottom left where it's the concentration in the two tissues, so that would be reality check number one, that the simple model is going to equilibrium and the concentration in the two tissues is going to the same value. Remember, our transfer is concentration driven, so it should go to an equilibrium concentration. This right-hand plot, though, is the total amount in each of the two compartments. You see the total amount in the compartments are radically different. The body's 13 times bigger than the blood compartment. So this should be a difference of a factor of 13. Let's see, we started off with 1 unit in the blood. And that was a concentration of 0.2. This one did the same one. Yep. Okay, so that's a very simple, that's just writing equilibration between the two compartments, given that the two compartments have different sizes. Oh, so that's what happens when you transfer a PowerPoint from one platform to another. You lose characters. So this is the mixing characters here are just a right arrow. I'm sure that's just the right arrow. So we're going to extend. So we just did these two red compartments. Now we want to extend it and add a source compartment. We'll call it the gut, and a clearance compartment that we'll call the kidney. These are a little bit different. We're going to assume that gut to blood and blood to kidney are unidirectional. There's no reverse process. So we just get a simple forward single or first order ODE with a gut to blood. And from blood to kidney, a simple first order irreversible transfer. So we need to add 2 more ODEs. We also need 2 new compartments, and we also need to initialize the values. We'll start off now with nothing in the blood and 1 unit in the gut and nothing in the kidney. So we'll go back and let's add 2 more compartments. Call it gut and kidney. We'll define their volumes be 1 liter for the new two new compartments, both being at 1 liter. The kidney, that's kind of an arbitrary value for the kidney. The kidney is kind of a hard thing to model in terms of concentration or even amount, because every time you urinate, you void it and everything restarts. But usually you don't worry too much about that. So that's just the terminal compartment where everything's going to collect. We then have our 2 new ODEs. Notice I wrote them a little bit. So we have exiting the gut, so we have a negative. It's entering the kidney, so it has a positive.
People shouldn't be shy about asking questions, because this is very different material, talking about how drugs and molecules move around in the body. These are very different questions from the ones we've been asking before. I think it's very important to see that this kind of modeling can be used in such a different application. But if there's anything that's not familiar, or terminology or ideas that aren't familiar, please don't hesitate to ask.
And our initialization, so we'll put 1 unit in the gut. And if we define the volume as 1 for the gut, there's just concentration of 1. And then the body, the blood, and the kidney all start off at 0. And then do a time course simulation, and it'll take considerably longer, not computationally, but you'll have to simulate a much longer period of time, because this is takes longer for things to percolate through this more complex model. So it might take several hundred units. I don't remember what I used in mine. And that is in the Dropbox, the PK example number 2. So people are probably hopefully just working through it. So we just go back up and we'll add 2 more compartments and initialize them both at 1. We need 2 more species. Again, these represent the same species, they're just in different compartments. And that is kind of an oddity in this kind of modeling. That your compound has a different name depending on where it's at. SBML actually has a facility for collecting up and saying that all of this X blood, X body, X gut, X kidney are all compound X. They're all instances of compound X, which is really handy. That means you can just annotate the species once, and then with the annotation for the compartment it's in, you can derive that this is, for example, acetaminophen in the liver. And then again, we need our substance only tags for our 2 new compartments, or 2 new compounds, same compound in 2 different compartments. And our 2 new ODEs, which are fairly simple. But in Tellurium, we also need to add it up into our ODE describing the state of the blood. But that's just the same as these two ODEs with the sign switched. The right-hand side of the equations with the sign switched. In other modeling environments, you wouldn't have to do this part of the equation because it would be inferred from the other equations. In fact, in Jarnac, it would be inferred as well if we weren't using explicit ODEs with the apostrophe on them. And then we have two new rate constants we need. So the K gut and the K kidney. Just this rate constant and this rate constant. Again, we don't have a good idea of what that should be. So we'll just define them as 1. And then our slightly different initial conditions of our material is going to start in the gut and the blood's going to start at 0. Okay, looks like everybody's got that. See if mine runs. Make sure it does. Yes, looks like it did. So you'll need some minimal plots. I got a couple of plots that I'm doing. The simplest one is just this first one that just plots everything. And since we have the substance only tag, we get both concentration in square brackets and amounts without square brackets. We've now got 4 compartments, so we have a total of 8 things. If we just plot the concentration in the blood and the body, our 2 original compartments, you see kind of some of the sort of what we saw before. Big swings in the concentration, but then it goes to equilibrium. Well, actually not. But big swings to start with and then dampens back down to 0. The amounts in the gut and the kidney. Your gut goes away quite rapidly. The kidney has an initial fast phase and then a slower secondary phase. The amount in the blood, which peaks pretty rapidly. The body peaks a little bit slower. It takes a lot longer to bleed back out of the body. So if we go back and look at it, so for instance, so the gut goes down very quickly. So this compartment is transferring out very, very quickly. But what happens then is it gets into the body, it gets into the blood, and then it gets into the body. And it takes a long time to bleed back out of the body. And that's why we have this relatively long tail on the body, and also a fairly long tail on the kidney. So that's what you get if all your rate constants are 1 and you start with 1 unit. We do have a much bigger body compartment than we do have a blood compartment, so that's reasonably physiological. But having all your rate constants be 1 is not terribly likely. And we haven't actually defined a specific time unit. There's a comment in the file, but you see it takes the fast phase that's happening in 10 units, and this slower phase, which is still kind of tailing off at 120 units, 120 time units.
Can you remind me of the reason that we initialize X gut to 1? Is that supposed to be like 1 as in a percent, or could we have also 1 as in like 100%, or could we have also chosen like 2? And maybe
You could, yeah, you could. And normally you would think about this would be grams. So that 1 represents a 1 gram dose. Or it could be a 1 mole dose, except for most molecular weights are up over 100. So I think grams are kind of the more natural unit. It could also be milligrams, some other mass unit. Acetaminophen, which we'll talk about more in a little bit, the standard dose is 1 gram. As far as drugs go, that's a lot. Estrogens used for hormone replacement is 0.6 milligrams per day. So a 1 gram dose is a pretty big dose, but that's what it takes for APAP.
Thank you.
Mm-hmm.
And I guess another, just to make sure I'm clear on this, the natural assumption of this model is that none of the volumes are going to change.
Yes, that's a very big assumption. And we're also assuming that forward and reverse transfer between blood and tissue is the same. So equilibrium constant is 1. So we're assuming there are no active transporters in the system, which for small molecules is actually a surprisingly bad assumption. It's an amazing number of small molecule transporters, both importers and exporters. And it actually becomes a pretty big challenge in chemotherapeutics and to a lesser extent in antibacterials, that they tend to develop exporters which actively pump compound back out of the cell again. And it's really hard pharmacologically to fight a pump that's pumping back out of the cell. You do also run into importers. There's a little bit of data that suggests that there might be an importer for acetaminophen in the gut and in the liver. So it's actually actively pumping compound into the cell. But that's the second big assumption, is that we don't have any active transporters.
Thank you.
Mm-hmm. So now we have enough to actually do a full PK model. Granted, we are doing gut absorption and kidney clearance, but to be fair, we could just change the word here and call it lungs, and this could be an aerosol pulmonary delivery. And we could change kidney to liver if it's being cleared by the liver. So in general, what we're really saying is there is some input source and there is some output source, and we always have blood and body. But with very minimal modification, this could be a topical, this could be an injection. If you were doing this as an injection, you would basically just set this K gut, call it K injection, to be a very, very big number. Everything is absorbed in 2 seconds, or however long it takes you to actually operate a syringe. If it was a subcutaneous dose, this absorption rate would be very, very slow compared to the gut usually. And again, you call it kidney, but it could be anything. Just a way in, a way out, and then this partition between what you can see, the blood, and what you would like to actually know about, which is concentrations in the body. So it's a very general purpose pharmacokinetic model, very reasonably simple. Surprisingly, people often say that give it enough equations, give it enough parameters, you can fit anything you want. Surprisingly, this simple model will break, and noticeably break, if there is some assumption that's not true. For instance, the compartments are not the same size. If you have an active transporter, if you have pumps, what will happen is when you try to fit data like this, you just can't fit it. There's always some systematic error in some part of this curve. So here's we saw this graph before. This is acetaminophen in human. The 1.4 gram dose is a bit big. Very characteristic ADME curve for an oral drug. Acetaminophen, if you're going to use it to treat a headache or fever, you don't want a very slow onset. To put that more logically, you want it to get into the body as quick as possible, because the person does not want to wait for hours while the compound gets into their blood so it can get rid of their fever or their headache. Other drugs, you want a much slower rise. Drugs like anti-cholesterol or cholesterol-lowering drugs, you're going to give it every day. It doesn't matter nearly as much how fast it gets into the blood, because you're going to repetitively dose it anyway. So from a pharmacological standpoint, adjusting, there are logical directions you'd like this curve to move depending on what it is you want the drug to do. And that's part of pharmaceutical drug research about how can you modify things to make this peak change. So in any case, this is the data for APAP. Like I said, you want it to rise very quickly. You see indeed it does. It peaks within an hour. In fact, at half an hour, you get a significant amount of the drug is in the blood. If it's in the blood, it's probably in all the tissues reasonably well. And then a relatively slow decay, which is good. You want the drug to hang around a while. Looks like half-life, clearance half-life of maybe 4 hours. So you might want to redose every 8 hours, 2 half-lives. You do want the drug or the curve to go down eventually. You don't want it to stay in the body indefinitely. There are a few drugs that do that. Tamoxifen, which is an anti-cancer compound for estrogen-dependent breast cancers, its terminal clearance rate is measured in months. So once you give a dose of it, there's nothing you can do except for wait for a couple of months for it to clear out of the body. With acetaminophen, if a person has an adverse reaction, if they can hang on for 10 hours or so, most of the drug will clear out of the body. So in the box, we should have a CSV file and also an Excel version of this data, these data points. So single oral dose, 70 kilograms, you get that curve. And as I said, we called our compartment the kidney. Acetaminophen is actually cleared primarily in the liver. Very, very little of it ends up in the kidney. Its clearance mechanism is different, but our simple model will still work. James tells me that you've done something like this before. This is, given this relatively small amount of data of the ADME curve, can we estimate some of these rate constants?
Well, we did this in the context of trying to estimate the doubling time and the decay time for population infections for COVID, looking at the infection rates in Italy, the United States.
So the nice thing about at least in this model, exit from the gut, so gut to the blood, and then blood into the kidney. These are just first order rate constants, which means they behave nicely. They have a true half-life. And if you can estimate the half-life, you can calculate, you can estimate the rate constant. So these two graphs, so this is just the early part of the ADME curve, and this is the tail part of the ADME curve, under the assumption that this rise is primarily absorption. And the last part of this decay is primarily clearance. So when you're out here at 10 hours, you're really not getting any more absorption. There's no rise going on. It's just clearing out of the body. So we can use this early part of the curve to estimate the uptake half-life and the late part of the curve to estimate the clearance half-life. We're modeling these as first order. If this is a true first order reaction, we can pick any point on the curve and take the halfway point and calculate a half-life. My clock is going to bing here 6 times. So given the uptake, we can estimate a K uptake of about almost 3 hours. Excuse me, yeah, that's a K uptake. 3 reciprocal hours, a half-life of a quarter hour, which is consistent with this. That point is at about a quarter hour. Take the reciprocal, multiply by the natural log of 2, and you get a K of 2.8 reciprocal hours. Do the same thing on our tail. Pick any point that we think is far enough out that we're not looking at distribution or uptake anymore. Take the halfway point, get a delta, calculate a half-life, take the reciprocal, multiply by log of 2, and get a clearance of about 0.2. There's a little bit of fiddling that we have to do. I can't click on this because we're working with clearance is primarily out of the body compartment, which is 65 liters in our model. This is primarily the gut volume, which we set at 1. So there's a little bit of correction for the difference between a compartment that's 1 and a compartment that's 65. So we're going to do two things. We're going to use these as our estimates for the K blood to kidney. And this is our estimate for gut to blood. And then we're also going to add this little chunk of code. It's going to load up this file called the Critchley data. And I can't highlight things, which I believe is in the box. And because this is primarily, can you type long lines of random characters and not make typos, you might want to just go and get the Model 3. And Model 3 is just Model 2, except where we've added loading the data. Did I actually plot it there? No, I'm looking at the wrong one. So Model 3, I don't load the data yet. Right. There it is. It's actually, my name's broke. So this is the file PK Example. PK Example fit. It's the same as Model 3, except it has the load command. In addition to that, load command up here in our rate constants, we plugged in our estimates. Actually, it's, yeah. And made a guess on this forward and reverse rate constants. And if you run that one, you should get this curve. If you do get, you can go to my slides. So this bottom right graph, so the human data is the blue line. The gold line is our model, just using our roughly estimated values of their observed half-lives, as well as picking a value for basically what our time unit is, and saying it was our forward and reverse rate constants for 360 for blood to tissue. That was finagled a little bit. It's not quite as obvious how you set that one. So there's a file name down here, PK Example 3 fit. Now from your little talks that you gave, your updates you gave at the beginning of the class, at least some of you have quite a bit of experience fitting data in Tellurium. So the thing to do next in this model would be to, instead of using our estimates of the rate constants and so forth, the partition rate constants and the, they're all rate constants, to actually fit it based on the experimental data. So right now it's these three four rather, K forward, K reverse, K gut, K kidney. K forward and K reverse, where you're setting to be the same number. So saying these are equilibrating, there's no active pumping. Concentration is just trying to equilibrate across the two compartments. But this 360, unclear exactly what that number would be and whether or not you'd get a better curve if you adjusted this number. And then these 2.6 and 2.8 that we extracted out of the APAP ADME data could no doubt be fitted better. Joshua made another file, which we have. Let's see if I can find it. Yeah, it's this one. One thing, I must have dropped the slide. This particular graph here showing the time, log 10 of the concentration versus time. Often when you see ADME curves, it'll be plotted on a log scale on the y-axis. I've been using a linear scale, but very often you'll see a log scale. The interesting thing, most characteristic thing about this particular presentation is that if your clearance, your final terminal clearance is basically a first order process, this tail will be a straight line. We get curvature up here at the uptake and distribution and metabolic phases, but clearance will dominate at the end, and it'll give this nice straight line. If this line is not straight, then your terminal clearance is not a first order process and something else is going on. For instance, you're getting clearance from more than one compartment, both the kidney and the liver, for example, and they're clearing at different rates and they have different compartment or different concentrations in the compartments. So you'll get a non-straight line out here at the end. But this is very characteristics of ADME plots, as well as everyone wants to plot them on a log scale as opposed to a linear scale. I prefer the linear scale just because I've been looking at first order rates for 30 years and it makes more sense than this. Plus the fact that most of this data down here, you probably don't actually care about. This is a log scale, you're talking about very, very low concentrations and your curve is being drawn using data that isn't really all that reliable. But in any case, so hopefully this would be an assignment. Can you fit these three parameters, since we're going to just say KF and KR are the same thing? A little more complex would be to actually try to manipulate the curve. So this was our very first graph where we marked the characteristic of the drug is the area under the curve, the time to peak concentration, and the concentration at the peak concentration. So how would you adjust these three parameters to move the peak to the right, to decrease Tmax, to increase or decrease the rate that this final tail goes away? Which parameters affect things most? Like, it's probably fairly obvious that your gut absorption rate is controlling this, and your kidney clearance rate is controlling this tail, and that in the peak area, all kinds of things are going on. Absorption is still going on. It's still distributing from the blood to the tissue and then back again. Clearance is starting to happen, so it's contributing to this curve. So this part of the curve, it basically has all the processes going on at the same time. Okay, so we'll end for the simple model, we'll end there. And this particular example is reusable because it includes the fitting routines. All you'd have to do is change your ADME data and rerun it. And this is, again, this is the fitting program. So this is how good of a fit it did after a certain number runs through the minimizer. It doesn't actually, I didn't put in what step that's in, but and there's after more rounds optimization. And see, that is better than our wild ass, well, our educated guesses of what the parameters should be, which actually isn't all that bad, which we can get better data or better fitting by working on a little bit harder. My ADME data, I did not include the error bars. ADME biological data in general usually has pretty big error bars, both as standard deviations and SEMs, standard errors. It would be somewhat arguable about whether or not these curves are actually different from each other. Because there is so much noise in the human data, the error bars here are fairly large. So you could argue that this is actually a reasonable fit. And the fact that you can get essentially a perfect fit means you're probably overfitting the data, at least partly. But it's a simple model. The quality of the fit suggests that the model is not missing any important features, like transporters. Okay, so that file is in there. That's reusable, and you can explore it a little bit at your leisure if there's anything useful that you can use for your projects. Now, to change gears just a little bit. So what we've been doing is single dose, which is what you do if you've got a headache and you take acetaminophen. You usually take a single dose. A lot of drugs, though, are multiply dosed, so cholesterol-lowering drug that you take once a day. An antiviral, where you're probably going to be taking it, you may be doing it every 4 hours for 3 or 4 or 5 days. Antibiotics are often twice a day for up to 2 weeks. So how does that change things? How does the blood profile change when you're doing repetitive doses? And this is a whole area unto itself. And I lost the, this is one of Bob's slides. I got to put his acknowledgement back in. But in any case, so this is repetitive doses. As you might expect, you kind of just get an oscillatory system. The peak width or the separation between maxima is how often you're dosing. After several rounds of dosing, you usually settle into an oscillation between a maximum and a minimum dose. This particular data set equilibrated really quickly. Usually it takes more than one dose to get this minimal value to settle onto a particular value. In a therapeutic environment, your goal would be to set up your dose of both the amount of dose and the frequency of dose, such that you spend almost all of your time in this range of the therapeutic window, the minimal effective dose and the maximum tolerable dose. Anytime you drop below the minimum effective dose, you have to worry about whatever it is you're trying to treat coming back. Antibiotics and antivirals in particular, and actually anti-cancers as well, you really don't ever want to drop below the effective dose, because you tend to start to select for things that are actually refractory to the drug. So this is fairly common problem in our model. It basically just be that at time such and such, you get another dose in your gut compartment. Where's my model? There it is. So t equals 0, you said there was 1 gram. You're going to add into your code at t equals 6 hours. You get whatever was there plus another gram. And then 12 hours, whatever's there plus another gram. And you'll just reproduce that oscillatory behavior. So repetitive dosing. Okay, there is multiple characteristics of a repetitive dose: is how often you're going to give and how much you're going to give. So this is Robert Stratford. The previous slide was also from Bob. And these are typical pharmacokinetic type challenges that pharmaceutical chemist and a pharmacologist would sit down and try and work out early on in the drug development process of which of these kinds of curves would be best for the system you're trying to do. These two graphs both show very rapid rises. So this is a well-absorbed drug. You'd get even more rapid rise if it was an injection into the blood. you'd give a slower rise if it was subcutaneous injection or a topical or something like that. So you can, to a certain extent, fiddle with the shape of the curves. In some cases, you're forced into a particular domain. Biologicals, proteins, DNA, antibodies, things like that are not orally active. You can't give them orally. They just won't work. They won't get through the gut, won't get through the stomach. So you're forced into a subcutaneous or some other injection mode, which means that you don't have quite as many options here because you're forced into an injection, which is going to give you this very, very sharp rise. And it's very difficult to keep within the therapeutic window when you have a very, very sharp rise. So antibodies, antibodies, insulin, growth hormone, these are all things that have to be given as an injection just because they just won't survive the gut, the GI tract. Okay, so that was the simple model and a little bit about multiple dosing. Okay, if it's okay, I'm going to move on. So I hope my screen is sharing. So more complex models from PK to PBPK. So PBPK is physiologically based pharmacokinetic modeling. Previously, we had a couple of boxes. They were pretty gross things like blood and body. In PBPK modeling, we're just going to make more boxes. And we're going to give them more descriptive names, and we're going to associate them with particular organs in the body. So this particular drawing here shows the thin line is the blood flow. And here we have a liver compartment with the amount concentration compound X in the liver. In addition, the organ is associated with a volumetric blood flow through the organ, usually represented as Q, in the subscript of the organ. So this is the blood flow through the liver. And so you got also blood flow through the gut, through the stomach, kidneys, heart, lung, brain, however many other tissues you want. You might have a peripheral compartment or a fat compartment, kind of representing the generic skeletal muscle and body fat, which tend to absorb things differently than other tissues do. However, now you're being more explicit about how you're linking the compartments in terms of a blood flow instead of just passive transfer between this, basically a stationary blood compartment and a stationary tissue compartment. So what's added is more compartments and more blood flows. So there are a lot of variants of PBPK models. These are two generic ones that are very similar to the one that we'll be using. The idea that you have arterial vessels, blood flows through the individual compartments, the individual organs or tissues, collects in the vein, back up through the heart, through the lungs, through the heart again, and goes around the loop. You enumerate the organs or compartments that you're interested in, and then you typically have another compartment we're just going to call the liver, or excuse me, the liver. Going to call other, everything that's not included. Just as a reminder, what this really means here is that we're going from these very large gauge vessels down to capillary blood vessels. And then the capillaries are recombining back up into very large gauge veins to circulate the blood back to the heart. So every organ is one of these capillary beds. Most of the time, we just have arterial flow into the organ and then flow out to the venous. Some organs, like the liver, receive, very few organs, have two inputs. So the liver receives blood from the stomach and intestines capillary bed. The liver also has its own arterial flow. So the liver has both a venous input and an arterial input, and then a venous output. So multiple variations. This particular one is using it as treating it as a Markov chain model, the individual compartments. That gives a very simple connectivity matrix, which is great if you're doing math. It's very difficult for somebody to back out what tissues and what flows these are. Got a heck of a lot of annotation on the model. So a Markov chain, it can also be done as, say, a Gillespie model, and any number of other approaches. If we get in a little bit more detail of the thoughts of a tissue, we have a large gauge supply going down to capillaries, which are in intimate contact with cells in the tissue. Those capillaries then collect back up into venule, which goes in a vein and returns back to the heart. You could conceivably come up with a PBPK model that actually treated each one of these cells as separate, going down a pipe, lining this one pipe here. We're not going to go to that level of detail. That approach, though, is taken in things like the intestine, where you might treat the stomach as a compartment, and then the first part of the intestine as another compartment, and the next part of the intestine as another compartment. And there the flow would be material moving through the GI tract. But each one of those subcompartments would have its own vascular supply. And now this bottom slide is actually really important, and we're going to gloss over a whole bunch of stuff. This box down here represents your compound free in the plasma. But small molecules tend to bind to plasma components, to things like serum albumins and things like, and serum immunoglobulins. So there's usually a fair amount of the compound that's in the blood, but it's bound to something, it's not available. In addition, we've been talking about the plasma concentration, but the blood is actually the combination of the blood cells and the plasma. And the blood cells are almost half the volume of the blood. So the concentration in the blood is different than the concentration in the plasma. You usually do all your calculations with the calculation in the plasma. In addition, though, as a further complication, some compounds will bind to red blood cells. Since that's such a big volume of the blood, a lot of compound can be tied up with the red blood cells. If it's just passively diffusing in and out, it just acts as a compartment that slows things down. If the blood cell actively binds the compartment, then it's a sink, and it's competing with the rest of your body for compounds. So we have these three boxes representing compound in the blood. That in turn is transferred into the interstitial space and into cells in the tissue. And in all of those compartments as well, there's also the possibility of having some binding protein. You have an interstitial binding protein, you have a subcellular or intracellular binding proteins, and those are all things that can suck up your compound. In some cases, they may be metabolic. It could be a cytochrome P50 or something that's metabolizing the compound. But in many, many cases, it just ties the compound up and keeps the compound out of the system. And you don't really detect these bound forms until the compound starts to wash out. And it gives you a very long retention time because it has to unbind from whatever macromolecule is bound to and diffuse out of the body. So there are a lot of other details that you have to take into account if you want to cover everything. There are, in treating a particular compartment, there's two limiting models. One is called the diffusion limited model, and the other one is the perfusion limited model. Usually people use perfusion limited. Perfusion limited is saying as blood flows through the compartment, it's the blood flow that's the rate of the blood flow that's limiting everything. And Doug is upset. The compound is essentially always at equilibrium across the system within that compartment. That'll happen when you have rapid diffusion. So small molecules that cross membranes easily, like acetaminophen, will usually act in a perfusion limited fashion. In a diffusion limited model, the slope step is the transfer out of the blood and into the tissue. And usually what's done there is you basically make your organ into two compartments, and you treat a static blood in a tissue compartment. This is a little bit more complicated. It can be done. It's not that much more difficult, though it does add a lot of extra parameters to your system. We're going to stick with the simpler perfusion limited model. Often, even if it is a diffusion limited process, the diffusion process is still fast enough that over the course of, say, 10 minutes, it behaves as if it's perfusion limited. And since biological processes usually take minutes to occur, if it takes a couple passages of the blood through the organ to get it to equilibrate properly, on a biological timescale, that's not very long and it's not really significant. And so the perfusion limited model still works. The other thing that's almost always assumed, and we actually assumed it in our first model, our simple PK model, is that we have a well-stirred approximation. Our compartment is always at equilibrium at every point in the compartment. You can see how that's actually a bit of a problem in a biological system, because what we're saying is that when a star enters our blue compartment, at the next infinitely small time step, that star is capable of leaving. If you're doing it as a star and using, say, a Gillespie formalism where you're treating individual entities instead of concentrations, there's a non-zero probability that this guy will exit an immediately small step later. And that's incorrect. There really should be some transit time through the organ. Again, that's usually ignored. If you can't ignore it, what you do is you generally generate sequential compartments. So you do a whole bunch of these compartments in a line to try to mimic that. And that's, as I said earlier, sometimes done with the gut, small intestine, sometimes done in the liver and the kidney and a few other organs. But well-stirred approximation, the concentration is the same everywhere within the compartment. Usually it's not a significant problem, though you always have to be aware that that's how we're treating it. Okay, so this is the basic equation, or the starting of the basic equation. It looks similar to the equation we had before. We have a compartment called C, and there's some amount of X in compartment C. Compartment C has a volume, so VC. The additional complexity, though, is there's some volumetric flow of blood through the component to the compartment called Q, used for flow, and the sub meaning compartment C. So each one of these compartments typically will be an organ or a tissue, and each organ or tissue has some standard volumetric blood flow through it and some standard volume. Okay, this is a place where units can really bite you in the butt if you're not careful. There's two ways. This is the standard simple equation I had on the previous slide. So the rate of change of X in the compartment is the mass, the mass of X in compartment C, is the blood flow through the compartment divided by the volume of the compartment times the amount in the compartment. It's exiting, so it's a negative sign. So the rate of exit is proportional to how much is in the compartment, but then this ratio. Sometimes people have a problem. They say, well, this is concentration and this is volume. I can convert that into a concentration term. And that's true. The problem is now in our equation, we have a concentration on the right and amount on the left. Furthermore, this kind of says, well, this should be a first order rate constant, but it's not because the units are wrong. This says liters per second, for example, as units, which are not the right units for a first order rate constant. So you have to be very careful about combining the terms and changing from an intensive to an extensive variable. So instead, the easiest thing to do is to just consider this ratio of the volumetric blood flow through the compartment divided by the volume of the compartment as being the first order rate constant. And it works because the units work. So this is liters per second, and this is liters. So the fraction has units of reciprocal time, reciprocal seconds, for example. So that is the first order rate constant for flow through a compartment like this. And that applies to biological tissues. It also applies for pumping clean water into a tank of dirty water and all kinds of other flow through a compartment situations. Again, with the assumption or with the well-stirred approximation. So given this is the first order rate constant, you can calculate the true half-life for how long it takes for half of the stuff to be washed out of a compartment as natural log of 2 times the volume of the compartment divided by the QC. So the reciprocal, this is the reciprocal of the rate constant. That's how long it takes to flush half the material out of a compartment. And it's a typical first order process, and you'll get a nice exponential decay. So if you're talking about a compartment that has nothing complicated going on, you can just use this simple equation. The volume of the compartment, the blood flow through the compartment, the amount of compound in the compartment at a particular time, and that is the exit equation. The entrance equation is a similar equation coupled to whatever the input compartment is, usually the arterial blood. Okay, so you got to keep track of your units. And this is for a compartment where nothing terribly exciting is happening. As kind of a rule of thumb, you don't want to, this equation applies to this arrow, and we only want to include this arrow in our model once. When we come to this compartment, we don't want to add this equation again. We don't want to have all our equations duplicated. So kind of convention, you just write your exit equations. And if you're using an SBML compliant tool and not doing explicit ODEs, that's okay because the tool will take care of collecting up all the individual terms. I don't think you actually have this file, I'm not sure. But this is reasonably straightforward. It's very similar to the model we did before. Just saying how fast does something bleed out of a compartment, starting with a particular amount in the compartment and a constant flow. And you get kind of what you expect, the concentration versus the mass curves, just this first order decay. And if you switch over to a log plot, you get a straight line. So it's always a handy thing to do. Check it on a log plot to see if it is first order or not. When you have experimental data, the model itself will always give that kind of a curve. The first order process will always give a log linear plot, or a straight line in a log plot. Okay, so a little more detail about how you might go about doing this. One approach that's kind of in between PK and PBPK is these very small number of compartments. An input compartment, here we chose lung, usually be the gut. An output compartment, here we chose the liver, could equally be the kidney, would be another logical one. And then to break the body up into 3 compartments. Rapidly perfused are things like the brain and the liver. So blood flow per volume of tissue is very, very high. Slowly perfused tends to be skeletal muscle and a lot of other organs that, unless you're exercising, blood flow is relatively slow compared to the volume of the organ. And then this is a common one. You will see a fat compartment. Many toxins are very lipophilic. They really like to bind to fat. They really don't like to be in water. So the drug will, or the toxin will collect in the fat in the body. And that affects a lot of things. And so this is kind of a very intermediate model that it takes into account this capability of the fat in the body to absorb significant amount of compound. Ultimately, though, when the dose is done, when the perfused compartments are empty of drug, when your source is empty, the fat will continue to bleed compound out over a long period of time. Tamoxifen that I mentioned earlier that has several month clearance half-life, it's because it binds to the fat and just gets stuck in the fat. Also binds to cell membranes and a few other lipophilic places. But so this is kind of intermediate. We're going to go to a little bit more the classical PBPK with more organs. However, we don't necessarily want to model all the organs. We'll be selective about what organs we model. Usually you pick the organs based on what you're interested in, and then include kidney and liver and gut, because that's usually your sources and clearance compartments. But if you're talking about a psychoactive or CNS active drug, then you definitely include the brain, but you might not include skeletal muscle, for example. Okay, so there's some detail, though, that comes in when you start talking about a compartment. Here's our original flow through a compartment equation. And this here, what we're trying to take into account is what we had up earlier, that the compound is also, we're measuring in the serum, but there's also red blood cells in the blood, the compound may or may not be bound to serum proteins. So this is a common form that you will see. Our Q or V and our X are what we've seen before. RB2P is a kind of an unusual way to express, it's literally the ratio of the concentration in the blood to the plasma. If RB2P is 1, that means the concentration in the plasma and the blood is the same, which means the concentration in the plasma and the red blood cells are the same. That's a frequent assumption that this is 1. It's not always true. PHUB is fraction unbound by protein. So this takes into account whatever serum binding there is. And PHUB numbers can be estimated. There are a number of small wet lab assays that will estimate PHUB without having to actually use an animal, just using serum albumin and other serum proteins. PHUB can be quite large, and even in many readily available drugs like acetaminophen, biologically readily available, PHUB can be 0.5, 0.6, 0.7 and have a pretty significant effect on the overall rates. And then finally, the most important one, this is KC is the partition between the blood and a particular compartment. So across all of your compartments, RB2P and PHUB are always the same, but this is the one KC defines partitioning in the compartment. So individual compartments will have their own KC, their own QC, and their own volume, their own VC. So we have the two basic equations. In the simplest case where RB2P, PHUB, and KC are all 1, this equation just collapses to the simple equation. But this one has the capability of including a lot of other effects. So this is the model that we published a few years ago. And like I say, it's very similar to many other models, drawn a little bit differently, but it's just drawing. It's flipped around. We have blood flow from left to right. PBPK people like to have blood flow right to left for some unknown reason. We have a relatively few compartments: lung, kidney, gut, liver, but mostly because we're treating an orally delivered compound, so we need gut. Compounds metabolized in the liver, and actually liver is what we were interested in. It's also cleared in the kidney. Rest is common, that we saw it on our earlier side. This is the rest of the body. So everything else is in this compartment. So this is actually, in this particular model, a very big compartment. The venous blood, arterial blood recirculating. Q arterial is the total blood output. So that's a well-defined characteristic of a species or of an individual, how much blood the heart is pumping. And then we have a Q for each compartment. So volumetric flow through the rest of the body, volumetric flow through the kidney, gut, so forth. These all have to add up to this value. These over here all have to add up to this, and they'll have to add up to this, and this has to be the same as this. So you have mass transfer constraints. In practice, what you do is you look up the arterial blood flow for the species, the body weight, and the gender or the sex, and then look up these that you're actually using, and then QRES is just gotten by difference. It's whatever's left over. Same thing with its volume, is just whatever's left over after you take into account your explicit compartments. We then have, as we had earlier in the very simple PK model, some uptake pathway. So here's the gut lumen, the first order absorption in the gut. We have clearance in the kidney, so that's taking compound out of the system. This was developed for acetaminophen, which is very extensively metabolized, and in fact, almost all of it is cleared via metabolic processes. So there's another ODE for the metabolism in the liver. So that hint again of only writing the exit ODEs, and then many tools, SPML-based ODE tools, will aggregate things properly. So how you actually go about doing this? We're only writing exit, so we're writing exit for the kidney, but not an entrance. The simplest case, the venous compartment, we can use the simplest equation. We're not really concerned about protein binding, It really doesn't matter if it's bound in the red blood cells or not. It's not being taken up by the tissue because there's no tissue associated with the venous compartment. So this exit is the simple equation. The same with all of these exits from the arterial. These are all simple equations. The compartments, though, have to have a more complicated equation. And in general, if you have to use the complicated equation for one of them, you have to use it for all of them. So if you need the more complex equation for the rest of the body, you also need it for the kidney and the gut, the liver, and the lung. So here we have our three other terms: our ratio of blood to plasma, our partition coefficient for that particular compartment, and our PHUB. And the R and the F are the ones that are constant throughout the model, and it's just the K that changes for each compartment. The Q you can look up. There are standard tables for the volumetric flow. Same thing with the volume. In this particular case, for the rest of body compartment, it does be by difference of total body weight and subtracting out the explicit compartments. And as we said earlier, if these things are all one, the complex equation just collapses to the simple equation. And sometimes they actually are all one. Not very often, but sometimes. The uptake or the source and sink ODEs sometimes can be complicated and sometimes can be simple. Absorption in the gut is usually pretty well modeled. Just a simple equation. It's actually even simpler because we don't even need the volumetric blood flow. It's just some first order rate constant times the amount in the compartment. These other two are actually exits, so they probably need a more complicated equation. The kidney has a specialized term for its filtration in the tubules called QGFR, which is a compound dependent parameter, but it's usually expressed that way. The liver will also have any exit, as any compartment exit probably will have to have a more complex equation. But they will tend to be similar. So basically now up to 4 kinds of equations: simple exit from a simple compartment, exit from a complicated compartment, entrance into a compartment, which is usually simple, and exit from a compartment, or clearance from a compartment, which is likely a more complex equation. This concept of allometric scaling. So this model changes a little bit if you're talking about a 70 kilogram person versus a 50 kilogram person. There's a big difference there in just the volume that a drug is going to be distributed through. So 1 gram and 70 gram, 1 gram dose in a 70 kilogram person is different than a 1 gram dose in a 50 kilogram person. So allometric scaling, many things scale linearly with body weight. And actually I should add a line here and say they usually scale with the lean body weight. For example, your liver volume is a linear volume with respect to your lean body weight. So you can set up an equation. The correct for body weight is you have some reference that a 70 kilogram person has a 1.6 kilogram liver. Well, so that's this equation here. This is 70, this is 1.6. You plug in the body weight and you get a new organ total, organ weight for that particular individual. Very straightforward. Usually those actually should be lean body weight, not body weight. Other things don't scale that way. And there's a lot of reasons for this. One simple reason is the diameter of a pipe into a volume doesn't scale the same way as the volume does. That is the BMI index, body mass index is a rough estimate of the ratio between your body surface area and your body volume. And those two things scale differently. And in a tissue, the diameter of a pipe into an organ can't scale the same way as the length of the organ does. So this is a common one. Again, you have some flow reference. So the blood flows scale with this power. Some reference flow, volumetric flow rate, and some weight reference. And you plug in your individual's body weight into the calculation. 3/4 power, sometimes you see 2/3 power. 2/3 power is really, really close to 3/4 power. The nice thing about 2/3 power is it says you take a body weight, which is a mass, which you can think of as length cubed, the volume as a length cubed. You take the cube root, and that gives you a length, and then you square it, which gives you an area. So if this power was 2/3 instead of 3/4, you're basically making some rough estimate of how you convert from volume to area. And the cardiac flow is dependent on the diameter of the area, cross-sectional area of the vasculature. So this is a common scaling factor. You will see different values here. Like I say, sometimes 3/4, sometimes 2/3. It actually doesn't make a huge difference. It's amazing how close those two values are when you actually do the calculation and then compare it to an extremely noisy real life biological data. So that's allometric scaling. It's almost always reliable if you're talking about the difference between a 70 kilogram human and a 60 kilogram human. It's almost invariably fails miserably if you go from a 70 kilogram human to a 30-gram mouse. And it can even fail 70 kilogram human to a 10 kilogram child. So you can't push it too far. Usually, though, hopefully you would have data in the other species, so you don't have to push the allometric scaling too much. Okay, so this is the model we were looking at. This is the one that was in the paper that had the front page of up earlier. 6 compartments plus 2 blood compartments plus a couple of input and output sinks. It's worth thinking about all the parameters that are going to be in this model and what parameters are dependent on the model and what parameters are dependent on the compound. So this is just a summary of, these are our variables, our amount of stuff in the various compartments as a function of time. So these are the things we're calculating. We probably have an initial dose in this list somewhere. The red parameters are model dependent. So these are things that are dependent on the species, the age, the gender, etc. And they're independent of the compound you're studying. And then finally, the blue ones are the things that are compound dependent. So if you have a nice, solid, robust PBPK model that you've got these all worked out for, it's fairly easy to take that model and just change your compound by changing these parameters. Usually, though, if you have these parameters, they're actually dependent on the model that they were developed in. So actually, that's the paper I was talking about. We're running out of time, so I'll move a little bit quicker. Just want to say,
You still have an hour.
Oh, really? Oh, 7 o'clock till 8?
Yes.
Okay, good. So most of these Ks are the partition coefficients between the liver and the plasma, the rest of the body and the plasma, the kidney and the plasma. The PHUB, and this is basically a partition coefficient in the kidney, or similar to a unidirectional one. This can often be measured in the lab, sometimes can even be calculated with reasonable accuracy. These partition coefficients are much more difficult to get. CL metabolism, you can often back out of a model if you've actually got experimental data. Ratio of blood to plasma can be measured experimentally as well. So about half of these compound-specific ones can be measured easily or estimated with reasonable accuracy. But the partition coefficients are the tricky ones. Red ones, you would all just have a set of parameters that are representative of 70 kilogram human or 30-gram mouse, so on. So that's the paper we published a couple of years ago. It was the best Society of Toxicology's best computational toxicology paper of the year. It has a PBPK model, a model of kind of a pipe model of a liver, and then subcellular reaction kinetic models. Actually, here it is. So this is what's in the paper, our PBPK model. This is blood flowing through a sinusoid in the liver, which is basically a capillary lined with the hepatocytes, which are the main cells in the liver. As the blood flows down through the pipe, compound diffuses into the cells. Inside each cell is a model of the metabolic pathways. APAP is pretty extensively metabolized, and that's the main clearance pathway for it. And that's our 3 scales, so the whole body, the organ, the subcellular. In our paper, this model is repeated 3 times. There's a version of the model for acetaminophen, and then 2 more versions for the 2 major metabolites, the sulfate and glucuronide. And those are just fed from the liver compartment. So if APAP is said to be converted in the liver, a certain amount of it at a particular time stat, it just appears in the, for example, sulfates ADME model. And there goes my clock again. So this is not an unusual system where you would have more than one PBPK model that represents your parent compound, as well as all of your metabolites. This is all of the transfers just written out, kind of, simple. An individual one. So this is in a tool I don't think you guys have seen. This is called Copasi, which is kind of graphical editor for these things. And J06 is from the rest of the body to the vein. So this is the exit equation for the rest of the body compartment. And there's its equation. It's got its ratio of blood to plasma, the fraction unbound, and the partition coefficient between the rest of the body. So it just has that entire set. And if you don't do explicit ODEs, usually the tool will collect things up. So this is the rate of change of the concentration in the venous compartment. Remember, the venous compartment is the one that's got all these entrances, and then the one exit to the lung. And so it has all these summed terms. So from the kidney, the cardiac, exiting to the cardiac compartment, the rest of the body, input from the rest of the body, input from the liver and the gut, so on and so forth. Capacity does weird things. That's why so it's concentration times the volume. So this is a mass equation. And it just collects them all up. And, Tellurium is basically doing the same thing under the hood. You just doesn't necessarily give a nice put of all the equations. So we should have this file in the distribution. I believe it's called acetaminophen PBPK XML. We could sit down and have you go through all of these equations, but it's a lot of equations and a lot of parameters and a lot of detail that you can mess up, and it actually takes a while to get everything working right. Okay, let's see if I actually have this one up. I think I do. Yes, this is it. So this is a version of the model that's in the paper. It's published in SBML, and it was converted by Antimony from the SBML into Tellurium syntax. I was just looking, yeah, so none of the comments propagate through, which is unfortunate, but that's the way it is. So we have, these are all the transfer equations defined as functions just for efficiency. We have our list of all of our compartments. We have substance-only tags. For species, there's only one species in this particular model, but it occurs in each compartment, so that's why there's so many of them, just like before. We have a set of assignment rules, and this is actually doing allometric scaling. So there is a body weight parameter. If you change the body weight parameter, everything in the model rescales. The flows through the organs rescales, the volume of the organs rescale. You see here's our 0.75 allometric. Here's a 0.75, whereas this one is just linear. The transfer equations, all of the initializations, including our dose. Arterial flow, excuse me, the volume of the arterial compartment is scaled allometrically because this is scaled allometrically. Our rest compartment is just or total volume, which is basically the total, the body weight, minus the explicit compartment. So the rest just gets whatever's left over. And do something very similar for the volumetric flows. The flow through the rest is total arterial minus our explicit compartments. These are scaling factors. So in general, the volume of the artery is 0.0357 of the total body. And these again are used with the body weight to properly scale the volumetric flows. The body, so this is a parameter. If you change it, if you change it 65 kilograms, the person just gets modeled at 65 kilograms. That changes all the flow rates and all the compartment volumes. This is our dose. And the dose is expressed in grams and then converted with the molecular weight to moles. So this is the value the model actually starts with. This is the variable that we change along with the body weight, and everything just rescales. So there's our fraction scaling factors for the flow through the compartments, and then all of our partition coefficients. Most are 1. Various other things, their time units, hours. And so that's the whole equation, that's the whole model. This particular one, and this should run, and it looks like I got output, so it looks like it did run. So there's everything on top of each other, concentrations. The venous compartment, just for an oral dose, so that should basically be the ADME curve. That's the same data. The venous compartment on a log scale is linear. The model doesn't have things interfering with just a very simple, basic first order clearance. And then we just get all the concentration in all the other compartments. So I think we're going to finish early. This is, hopefully this file is on the server, antimony PBPK antimony, excuse me, acetaminophen PBPK antimony. So we can do things like, I don't use this software very often. Jupyter Notebooks, that is. We go up, looking for my, let's take a value here. 0.12 millimoles at Cmax. And now we're at 0.1, almost 0.16 millimoles. So maximum concentration in the blood went up by 25-ish% when I decreased the body weight from the original 70 down to 50. So it's great for poking and prodding. These parameters were actually fit to the acetaminophen data. So this is actually a reasonable results for acetaminophen. It's at least close. So I'd like to see if everybody can get this running. And hopefully it is actually in the folder. Yeah, there it is. If you need a very Well, it's a reasonably complete model, though it is somewhat liver-centric. As a starting point for any drug dose, this would be a reasonable model. So Josh wrote, starting with this model, this is from our earlier table. These are our fittable parameters. And using this data, can we fit this model? And I don't think we have that one set up. Clicking on things that makes it slide. Let's see. The thing I wanted to mention is there are a couple of packages specifically for doing PBPK model. There's one called SimSip. There's at least 2 or 3 more. They're all commercial packages that have things built in like volumetric flows and tissue volumes for different species. They're very nice packages, but they're also typically very expensive. Sometimes they have a student version, often not. The more traditional way of doing PBPK modeling has always been to code it up in R or MATLAB or Python or something else. Tellurium is a little bit better way of doing it. Because it was actually made for doing this kind of modeling, even though it was actually made for reaction kinetics. The PBPK is very, very similar, just a set of ODEs. However, Tellurium still has the limitation is that you can't really annotate a model in Tellurium. And let me check on something real quick here. So a model in Tellurium or in R or in MATLAB is really not a knowledge resource. It'd be very difficult to write an automated process that could extract knowledge out of these models. It's difficult enough for a human to reproduce it. You need both the, say, Tellurium code plus the paper that describes what all the variables are. You hope that the variables are names that you might be able to sort out, like CART, concentration in the arterial compartment. But in many cases, that will not be true. And it'll be very difficult to figure out what's going on in the model and what is supposed to represent what. So I was going to real quick pull open this first. So this is Kapasi is just a tool, a general purpose tool for doing ODEs of this type. Will read and write SBML files just like Tellurium will read and write SBML files. So you can communicate between the two platforms and several other platforms via SBML files. But the nice thing about using the full power of SBML is that you can add annotations to a model. So this is this same model in Tellurium, and you can add, we have free text. But you can also give names to compartments. And this model doesn't have it. Great, I pulled one open that doesn't actually have it. Yeah, because this is a variant. But I will explain what it would mean is that, so we have a species called CART, that you can add an annotation and link it to an ontology like KEBI for small molecules. Or ChemBL. Your compartments can be annotated in a similar way and pointed to, say, foundational model of anatomy and say that this is the gut compartment. So that directly links a little bit more human readable description to a variable in your model. So there are some advantages to working in tools other than Tellurium, especially in terms of annotating your model. So this model that we've been doing in its original version, the version that's available in biomodels, you can extract things like concepts like acetaminophen is metabolized in a phase 1 metabolic reaction because of all the metadata and tags that are associated with the model. That's much more difficult to do if you have a Tellurium version of the model where you've lost all those annotations. And it's unfortunate I don't actually have the right file handy. Nope, I don't have it handy. Okay, so
Which one are you looking for?
well, I'd have to go and pull it down from biomodels.
Oh, it's not one of yours. Okay.
No, yeah, I'm pretty sure I don't have it in there. If the model ever goes from Kapasi to Tellurium and then say from Tellurium, you lose all the annotation. So that's actually a challenge in this area of, there are a lot of tools that will run the models. There's somewhat fewer tools that'll build a complete model. And there are no tools that I know of that can do a full round trip. In Kopasi, you can define, you want to do parameter fitting. Well, that's a function in Kopasi. If you save it as a Kopasi file, it'll save your data and everything else that you decided to do. If you then save that Kopasi as SPML, you lose that curve fitting capability. And if you go back into Kopasi, it's lost track of your data file and all that those kinds of things. I am going. So everybody should try to load up this big Kopasi and give it a run, and try tweaking something simple like the body weight first, and then try tweaking something like there's a parameter called CL metabolism. If I find it, this one. This particular model treats the metabolic pathway in the liver as a single ODE, and that's clearing acetaminophen, doing all the clearance essentially in the model. If you significantly reduce this number, the APAP stays around for a very, very long time. In the meantime, I will go get the full full PBPK model.
Jim, how's it going here?
Okay. Has anybody
What we're seeing is
had
your
any
Copasi.
luck getting?
What we're seeing is your Copasi screen.
Yes, because I just downloaded that file. I wanted to find the annotations. So people should be trying to run the full model. And I'm trying to find this particular file. We could ask, has anybody been able to get the file to run?
This most recent model, yes.
Could you say that again? You didn't quite catch that? The full model or the littler model? There it is. I think I just crashed Copasi. Not surprising. So just a few final ones. If you got that model running, so it gives you something that you can prod and poke and give you the basic structure if you want to do a PBPK model. Usually, if you have a set of ADME data like this up on the upper right, you can get a reasonable and usable fit. It may not be correct in some details, and the model might be underdetermined. But that's something that you can explore, and it's actually interesting to know if the model's underdetermined or not. Frequently, ADME data is pretty noisy, though, and it frequently has trouble telling the difference, ruling out a particular model structure just because the experimental data is so noisy. So kind of how this is used, kind of a practical matter. One common use is to start off with a model in rodents or whatever your small experimental animal is. I think what needs to be added to this figure is there should be one more column to the left that has a microtiter plate. And you think about doing a PBPK-like model even in a microtiter plate. Granted, it wouldn't have lung and liver and such, but it would still have plastic wall and medium and cells, which all are parameterizable and all can interfere in the assay. I mean, it's not unusual for drugs and toxins in particular, to bind to plastic. So if you're doing a tox screen in a microtiter plate, there's a good chance that the toxin is actually binding to the plastic in the microtiter plate. So you can imagine having another column over here for your in vitro microtiter based or glass based assay. And then you develop your PBPK model based on that particular species, calibrate it with the data you have available there. If your model's underdetermined, it's much more likely that you can go back to your experimentalists and say, I don't need concentration in all the tissues, but if you give me the concentration in a particular tissue and this particular tissue, it would help resolve and refine the model and select from alternate models. But then to move to rescale everything and move to a human model, and at least get a first pass estimate of the ADME curve in humans based on the animal data. We'd probably want to incorporate new data, such as any metabolic data you might have from, say, human hepatocyte assay or something else. You may have some data that can be added in as you go to this step, but likely the model will be off a little bit. And then finally, to generate a suite of PBPK models to represent a population. So now instead of trying to predict an individual response with plus and minus confidence bars, now you're trying to predict the spread across a population. And we did that in our paper and simulated 1,000 people, looking at how much dispersion you would get in the response and what's a reasonable estimate of what the worst case is in terms of the person that would have the highest blood levels versus the person that would have the lowest blood levels. And actually the person with the lowest blood levels, the PBK provides an estimate of how much is in each tissue. And it turns out that the blood level is low because it's high in the tissues. So what is the 1 in 1,000 person? How much higher would the drug concentration be in the tissue than it is compared to the average person in the population? And conversely, what would be the person that had very high blood levels, therefore very low tissue levels, and are probably non-responsive to the drug, and perhaps refractory to any toxicity as well. So a suite of PBPK models to represent a population. If you have data on variability in, for instance, cardiac output, then you can directly use that data. If you have direct data, perhaps from genomic studies about up or down regulated cytochrome P450s or transporters or any number of other things that might be involved in your compound, you could build that into your population model. Have an individual with a high cytochrome P450 level, another individual with a low level, and see how much that affects the model, which is something that's very difficult to answer a priori and generally would have been done in a clinical trial, which is very, very expensive. This is a homework we had done before, and I think that was my last slide, yes. So one thing you could do with this model, calibrated model, is to say, earlier I had showed the repetitive dosing, and that slide was focused on staying within the therapeutic range of the compound. So that you've always got enough to have some therapeutic effect. Antiviral is still enough, even at the low level, to inhibit viral replication. This is a little bit different question. This is what happens if there's a toxic level, and you want to get as high up into the therapeutic effective range as you can without ever creeping into the toxic level. So generate a model that will actually explore that. How high can we go in initial dose, and how much can we, I think actually the problem says just assume a 6-hour gap. Try to design the best dose that won't go into the toxic level. So this is a real world type problem. It would be a little bit more relevant if you then said, well, instead of doing an individual, let's do 1,000 individuals, where each individual is a little bit different in their partition coefficients, in their blood volumes, in their organ volumes, in their body weights, and find out how hard we can push the dose without getting 1 in 1,000 person that's going to have a toxic effect. Because 1 in 1,000 is more than bad enough to keep a drug off the market. You would never be able to get it on the market if it had lethality at 1 in 1,000 people. Unless it was an anti-cancer compound, then you might be able to get it on the market. Certainly not for something that's used to treat headaches and fever. So I think that's about everything that I have. Does anybody have any specific questions? I know there's a lot of more complexity. We didn't talk about drugs that are actually inactive in their prenatal form, but instead are metabolized into an active form. A lot of antivirals are metabolically activated. Didn't talk about that. Let's see, anything else in particular we left out? There are a lot of other details that could be included. It's surprising how much information is embedded in the ADME curve. There's more data in this curve than you would think. And I think this data set has something like 12 data points, and that's surprisingly a lot of information in 12 data points. We have, looks like 9 fittable parameters, which you would think would be pretty difficult to fit 9 parameters with 12 data points, especially if some of your data points are like your 0 point, which don't have a lot of information. But indeed, this data is good enough to extract out pretty good estimates of all of these parameters. Backed up.
That was a lot of material to cover in one lecture. But so is that what, as far as you wanted to go, Jim? Giuliano, did you want to?
Yeah, I think so. I wish I
Go ahead, Jim.
Oh no, I said go ahead. Go ahead, Julia. I was just going to see if I can find this I think Biomodels has corrupted these files, but that's neither here nor there.
On my end, I guess I could try to show quickly how to make a new nanoHUB tool.
That would be great.
So yeah, let's do that then. Share. Okay, so you're probably more than familiar with nanoHUB, I'm gonna guess, in this class. So I'm gonna be honest, I'm not that familiar with creating new tools that work with Jupyter notebooks on nanoHUB, but I think the steps are pretty much similar to the steps with CompuCell. So what you want to do is come here on resources on nanoHUB. Then you're going to see the upload publish option. And you're going to publish a resource, your tool model. And finally here you can find tools. And we're going to stay in this page for a bit. And what you actually will have to do is you're going to have to host your model on GitHub. So in any case, you have to create a GitHub account and download Git Bash or something. Then what you want, so there's a lot of so with your models, the only thing you need for them is the Jupyter notebook itself, right, to run them. But when you actually go to host them on nanoHUB, you do need a lot of other files. And I've set up a repository with them that you can just copy. Just trying to find it here. here. So what you want to do is download all of the files there. And then you only need to change 2 or 3 things. First thing you're gonna have to change is, well, the actual notebook. In here I have just the notebook that opens when you open Tellurium, which just has the import Tellurium cell and an empty cell. So you're gonna replace this by your file with whatever name you want. Not having spaces in the name is definitely a good idea, probably. And then and I do have the instructions here. So if you're not following, that's all right too. And the other thing you're gonna have to do is come here on the middleware folder and change this invoke file. So we can see here that this third line, which is the first line that actually says something, is calling that tellurium.python. What's the name? Notebook. So you're going to have another file not called Tellurium. So you just need to put the new name here. You're also going to have to change in here. Yeah. So you're also going to have to change this -t Tellurium here, because this is the short tool name that you give your tool. So here, the first space is for the short tool name. And it should be 3 to 15 characters, and it cannot be changed. No spaces. So pick wisely what you're going to call your tool. That's not actually the name of the tool that people will see. It's going to be part of the URL only. The title will be the name that people see. So yeah, after you've replaced the notebook by your project, changed it here and the name here to whatever you're going to call your tool, you put in some description. You're going to tell nanoHUB that you're going to host your repository on GitHub, and you're going to have to paste the URL to the repository. And it's not this URL, as you might imagine, but this URL here in HTTPS. So for those that are not familiar with GitHub, this is, you can either download a repository as a zip, or you can actually download it as cloning from GitHub. And this here is going to be the URL that you're going to paste here. You're also going to have to tell them that it's Jupyter and permissions for people to use them. And that's pretty much it. Then you have to wait for nanoHUB to do their side of stuff. And eventually you're going to get a message on nanoHUB. Saying that your tool was installed or updated, I can't recall. And you're going to be presented with a page similar to this one, where you can actually tell nanoHUB to launch the tool. So this was one of my tests to get a Jupyter tool up, and it doesn't work, and it doesn't throw any error. It just doesn't load. But I'm pretty sure that this repository should solve all issues. Then after you've tested that your tool opens and that it runs, you just tell nanoHUB that it's working, and you're gonna give it a version 1.0, and you're gonna have places to describe your tool further if you wish. But yeah, that's pretty much it. Questions?
Not right now. Thank you.
Yep. If you have questions afterwards, I'm gonna put my email in chat, and you can just email me.
I appreciate it.
No worries.
Okay. Is there anything else that you want to go over today before we break? I have us down for Mercedes, Tyler, and Kali speaking next week, and Jeffrey, Antonio, Devin, and Brian speaking the week after that. And I'll send out a reminder of that. I know today was a little bit of a rush to get through a lot of material. I've got some slides which go into some of the issues that were discussed today in a little bit more detail. There's actually a collaborator of ours up in Indianapolis who teaches a whole semester-long course on what Jim was talking about just today. And if people are interested in the idea of a career in pharmaceuticals, for example, this kind of modeling is used, as Jim says, in drug development. It's used in FDA certification. And so it's actually, the models can get very detailed because, for example, your gut, where a drug is absorbed in your gut makes a difference. And so there are very detailed models of, for example, how a pill, everything that happens to a pill from the moment it enters your mouth to the time it's eliminated in your feces or your urine. So there's quite a bit that can be done there, but I hope you got at least a little bit of a flavor for this. Juliana, maybe you could just show them quickly in the last 5 minutes your model, because we didn't tie it back to COVID.
Yep.
And so Giuliano actually has been working with the team in Indianapolis at the medical school on using this kind of model to understand remdesivir dosing. So why don't you just show them very quickly some of your results?
Sure.
Because I think that'll tie it all back to close the lecture part of the course. It would be nice to come back to COVID.
Yep. I'm just pulling them up. Here. So Jim mentioned that antivirals usually have to be metabolized inside the body to work, and that's the case for remdesivir. So the guidelines for remdesivir up until a few weeks ago were to give a single dose every day. And we can see here that way before the next day, the levels of remdesivir itself go to 0. But if we actually take into account its metabolites, then all things are good. So remdesivir needs to be metabolized because the actual active thing that is going to stop COVID doesn't permeate cells very well. So they created an extra part on the molecule to give it good permeability. And we can see here, so this graph here is of the metabolites, and the one that we care about is available 4, which is the active one. And although the remdesivir goes to 0, the active metabolite doesn't, but it takes a few days to build up until it's at a steady oscillating level. Not going to talk about how remdesivir works or anything like that, but so this is just a PK model, and with the equations that I'm sure you are also used to by this point of the course. And we also have remdesivir acting on the virus. I just said that I wasn't going to say how it works, but I'm gonna. So remdesivir works by attaching itself to the elongating RNA that is being created inside the cell. So this is the viral replication model that we used in our big COVID model. And this part of the viral replication is the one that is acted upon by remdesivir. So if we look at the second term here, ignoring the fraction, we have exponential growth of the RNA. It's going to saturate because of the fraction, but still exponential growth. And the maximum growth rate is given by this Rmax. So the way we are modeling remdesivir action is by changing Rmax through a decreasing Hill equation. And that reduces the maximum rate. And we are wondering if the oscillations, depending on the dosing schedule, are enough for COVID to spread in between doses and render the treatment ineffective. And here are some preliminary results. Red is bad, where all of the epithelial simulated patch of the lung, we don't simulate the whole lung, so all of the epithelial cells in this patch die, or are infected rather, by the end of the simulation. And green are simulations where most of the simulated tissue patch is still healthy. And top and bottom is just changing when the first dose is given. So top, it's given at the same time you are infected by COVID, which would be very lucky. And you're probably we're planning on doing some prophylactic treatment and started it just in time. And here given after 2 days. And we can see that giving it later, the area of bad results increases. And so what is being varied in these graphs from left to right is the dose interval. So 24 hours is what the recommendations were. And on the vertical is how potent remdesivir is. So we can see that for 24 hours, we'd need a very potent remdesivir. Whereas if we give it more frequently, we can have the luxury of not having such potency. And same kind of idea here. Here we are. And yeah, and this is not a PBPK model, it's just a PK model. I don't have the gut or anything, and remdesivir is given IV, so no need to go through the gut. But yeah, that was it.
Okay, thank you.
So
Well, I
easy to do
guess,
that.
go ahead.
Somebody should do that for dexamethasone.
Yep. Yeah, but first we need to improve our immune response model.
All right. Well, thank you, Giuliano. Appreciate you doing that. Thank you, everybody, for being patient. I look forward to talking to you if you want to work on projects between now and next week. And we'll see everybody back Tuesday of next week for the first round of final projects. I'm very excited to see what people have come up with. If you have any questions about this kind of modeling, please feel free to talk to Jim. If you want to think about how to integrate this kind of model into multi-scale simulations, we can talk about it with Giuliano and also with Jim. Okay, thank you, everybody. See you next week then. Good night.
Night.
Thank you.
Thank you.
Thank you.
Thank you.